where we imagine that we have a tank that has some shape to it, maybe a cylindrical tank or maybe something like an aquarium, okay? Like here it says the tank in the picture is completely full of water. All right, so that tank right there, 4 by 2 by 3. And we want to calculate the work done in pumping the water out of the tank, or maybe pumping a certain amount of the water out of the tank, okay? All right, so there's two things about it that make this harder than the first problem that we did. So again, what was the first problem that we did? First problem was if you have a force moving something, okay, and the force is of constant magnitude and it acts in the direction that the thing is moving. Well, so that wouldn't be true with this in the sense that the distance that I move, like if you imagine that the water is getting lifted up out of here in layers, okay? So I know if we put an actual pump and a hose in this thing, the water might be swirling around a little bit as it goes in the hose and out the tank and through the pump and so on. But for us to do this in a way that involves calculus that can be done on paper, then we're going to have to think that, well, the water gets like moved up one layer at a time. All right, I know that might sound weird and impractical to you, but that's the way we conceive of it in order to make it something doable by calculus. All right, so this layer of water at the top doesn't have to move quite as far as that one, and the layer of water beneath that moves a little further, and the water at the bottom has to move the furthest to go out of there. So it's the distance part that's different everywhere in this tank. All right. Okay, let me show you how we set this up. Imagine that, again, for the sake of conceiving of a way to do this problem, imagine that I put like the XY plane and I impose it on this tank. All right. And I just use the XY plane because that's something that's familiar to us. Everybody knows what the XY plane is. And what we do is we take so much of calculus is done in terms of things that are extremely small. All right. Imagine having like a very thin, like unimaginably thin slice of this tank. And we're going to do our math based on that. So this slice right here, it's 4 feet wide, 4 feet this way. It's 2 feet this way, okay? And I'm going to say that the thickness, now this is the tricky part, because I said this is like thinner than you can imagine, super thin. I'm going to say the thickness is dy. All right? Okay. That's going to seem weird, but okay, that's how you do it. So here's how we do it. We calculate the weight of the slice. Okay? Which, how much does this slice weigh? Can you tell me its volume? Well, it's 2 by 4 by dy. Okay? So that's the volume of this imaginary slice right there in cubic feet. And it turns out that water has a certain density to it. Water is about 62.4 pounds per cubic foot. So this number right here gives me the weight of that slice. And why would that be important? Well, because in terms of a force making something move, like if you were going to pump the water out of this tank, the water's got to move. There's a force applied to it. And it's lifting it, it turns out. All right, so in the case of lifting something, the force, we'll do it this way. The force that's required to lift something against gravity is going to be its weight, all right? So, okay, so that's why it's important to know the weight of the slice. So this turned out to be, I think that's about 500. Let's see, 2 times 4 times 62.4. So 8 times 62.4. So that's 499.2. okay, times dy pounds. All right, so that's the weight. Now, what else do we need to know? The weight's like the force. What's the distance? How far to the top? Where is the top? Well, it's 3 feet tall. The top is 3. So the distance to the top, as it says that we want to pump the water just over the edge, just to the top. At least here, it doesn't say how far to, or what's the work to pump the water 3 feet above the tank, but just out of the tank, just over the edge. The distance to the top is going to be 3, like how far is it from here to here? It's 3 minus that spot, 3 minus this location. And say that this is on the y-axis. It's going to be this point having a y-coordinate, 3 minus y. So the distance to the top is going to be 3 minus y feet. Okay, so there's the force and the distance. You can calculate the work done by knowing the force and the distance. Okay, all right. One more thing about this, like imagine that I drew this slice right here. Imagine that I put it at the 1 mark on the y-axis. How far would it be to the top? Well, it would be 2 feet to the top. Well, what's 3 minus 1? It's 2 feet. That's why you do it that way. Okay. Now, from here, here's what we do with these. The work is going to be an integral. In here, it's going to be force times distance. All right. In my case, the force is going to be the weight. So that's 499.2 dy. And the distance is 3 minus y. So it's just those things are going to go here for the problems that involve pumping water out of a tank. That's how it's going to work. So let's put all that together, the force and the distance. I'll do 499.2 times 3 minus y dy. Okay. So from there, let's do the bounds. So the bounds are going to be like from, they're going to cover what portion are you pumping out. Like all of it, that would be from 0 to 3. If I say the top third, well, you know, this is 3. The top third is like from 2 to 3. And then the 2/3 below it, that's from 0 to 2. So this is going to be 2 to 3. All right. So on the y-axis, the span is from 2 to 3. You see how I put the coordinate system on there? So the top third of the tank, that would cover the y-axis from 2 to 3. So I'm going to just point to the bounds and say, oh, that's the y-axis. That's how that works. All right. And then we work the integral. Okay. So probably not that hard to do the integrals. Like we've done way harder integrals than this in our time in calculus 2. So here's what I'll get. I'll get 499.2. The antiderivative there, 3y minus y squared over 2. 2 to 3. Okay. So I'll have to do some rounding and so on, but here's what I'll get. Here's what I get when I put 3 in. So I'll get 4.5. Here, I'm just going to write this way to make it easier for me. 4.5 times 499.2, and then I put 2 in. I'll get 4 times 499.2. Okay. And then, so this will end up being 499.2 times 0.5, 249.6. So that'll be 249.6. The units will be foot-pounds. All right. Okay, so that's how you do it. So it's, I don't know, I would say it's probably to most people seems pretty far removed from the first kind of problem we did. Where did I start to do? So well, work is force times distance. All right. And so you tell me the force in pounds. You tell me the distance in feet, for example. I multiply them together, and that's how you do it if a constant force acts in the direction of motion. Well, the water pumping problems, there's just more happening there. The distance that every little layer of water moves is different. That's why it turns out to need to be an integral. Okay? All right, so now say that I have a variation real quick on this problem. Calculate the work done in pumping all of the water over the top of the edge. That means like the span on the y-axis of the layers of water that I'm pumping out is going to be from 0 to 3. So in this case, it's going to be the same as far as what this part is. It's still going to be 499.2 times 3 minus y dy. But then the bounds for the integral, the span of the region that's being pumped out, is 0 to 3 instead of 2 to 3. Okay, that would empty the tank. All right. Okay, so now then if you can do this one, then this one should be a problem. I want to mention that the bounds are different in what they were. All right, so let's do one more where the tank has a different shape to it. So consider this one. So a tank has a conical shape to it this time. It's a conical tank standing vertically, large end at the top. The tank is 6 feet tall and has a radius of 4 feet. So at that point, then you're just kind of describing something like, all right, there's this cone-shaped tank and like so, like that, okay? And then the radius here is 4, but it's 6 feet tall, so it's a pretty big tank. And it's got to be supported by some kind of legs or something, but that's what it looks like. Calculate the work required to pump all the water over the top edge. So it reads like the last one, but the shape of the tank is different, and that will change a lot about it. It's not going to change the general approach that we take this imaginary slice of the tank, we calculate its weight, meaning we find its volume, its thickness will be dy. We take that volume times the density of water, given that water weighs 62.4 pounds per cubic foot. And then we, calculate the distance to the top of that slice, which will be the top minus y. All right, so we're still going to do that, and we're still going to put that in the integral and have the bounds and so on. But that this is a cone, that will make it a little harder. So let's do it like this. I'll impose the y-axis on it again. Okay, and the x-axis, so here's x, here's y. And what I know about it is, I guess, like if you could imagine that this is a 3D object, but as I put the xy plane on there, that this is a line that makes the contour of the cone. This is a line that's on the xy plane. And it has this third dimension to it all the way around, though. This point right there of that line, given that this conical tank is 6 feet tall and has a radius of 4 feet, this would be 4 and 6, right? That's how you get to that point. You go up 6 and you go right 4. All right, so we've got that. Now, I need to take a slice of this tank. Right there. See that slice? And it has a thickness to it. dy. That's the thickness. And it has a radius to it. So what's the radius? Well, that's the hard part. The radius of this slice varies up and down the tank. If I had drawn it up there, it would be a lot bigger than if I had drawn it down here. So here's the way that we conceive of the radius. So first of all, if I was going to tell you what the weight of that was, it would be like this. What's the volume of this slice? Pi r squared times dy. Why is that? Well, this cylindrical disc right here, this very thin slice of this tank, has a thickness of dy, and it's otherwise a circle. It's like a little cylinder. It's like a coin or something. Its height is dy, and its radius is r or something like that. So this would be the volume of it in cubic feet. And then I would need times 62.4. And what's that? That's the density of water in pounds per cubic foot. So like generally, this is what I need to do for this one. It's just we're not clear yet what the radius should be. All right. So this is the volume of that thing, pi r squared dy. That tiny thin cylinder right there. That's the volume of a cylinder, pi r squared times the height. There it is. And then that's in cubic feet times the density of water in pounds per cubic foot. So but what's the radius? Well, okay. So is there a way to get the equation of this line right here? I think if we can do that, then we can figure it out. So see this line right there? So what's the slope of the line? It goes 4 to the right and 6 up. So that would be 3 over 2. Y is equal to 3 over 2x. Okay? Let's try it out. So does this line, in fact, have that point where x is 4 and y is 6? Let's see. So what's 3 over 2 times 4? It turns out that that's 6. Okay? All right, so this will do it. And isn't it true that the radius of this disk right here is the x-coordinate of points on that line? Okay, it is. I mean, when I go like this and make the radius, I'm going to the right. I'm going straight to that point. It's the x-coordinate of a point somewhere on that line, depending on where this disk is. All right, so let's say the radius is going to be, say you solved it for x. It would be 2/3 y. All right, that's what we wanted. So let's update this. The weight is going to be pi r, which is 2/3 y, squared dy times 62.4. Okay? All right, so there's my weight, and then my distance to the top. That's going to be 6. Where is the top? 6 on the y-axis minus y. 6 minus y. All right, now that's everything that we need. Let me put it all down here. Okay, so the work required to pump all the water just over the top of that tank is going to be the integral, whose bounds are the span of the tank on the y-axis. That'd be 0 to 6. Otherwise, I'm going to put the weight times the distance. Okay, now let's do a little bit of combining here. As far as numbers go, I'm going to get 4 over 9 pi. So I'm going to get this from 2/3 squared. I'm going to get a 4 over 9 of pi. I'm also going to get 62.4. I'm also going to get 6 minus y. I'm also going to get y squared and dy. I think that accounts for everything. So I got the pi, 2/3 squared. That's 4 over 9. 62.4, I got that. 6 minus y, I got that. And then y, see, this whole thing gets squared. I'm also going to have a factor of y squared. Okay, so let's do this. Let me pull all these constants out because it just seems convenient to me at this point. I think I'll go ahead and multiply that 62.4 times 4, though. So let me tell you what I get. So 249.6. So 249.6 pi 9. All right. 0, 6. What's left over? I combined all this into that. And I'm going to have 6y squared minus y to the third among these. And then dy. All right. So, okay. Working the integral. Carry this constant down. And I'll get this 2y to the third okay, minus y to the 4th over 4. And then I'll go from 0 to 6. All right. So 0 is not going to give me anything. I just got to do 6. So 2 times 6 to the 3rd power, all right, as far as that goes, minus 6 to the 4th power over 4. And that number turns out to be 108. All right, so this number is 108. Now let me round my final answer. Got 108 right there, times 249.6 times pi, and then divide by 9. And I get 9409.7 units, foot-pounds. Okay. And then we're done. Now, so it's probably not hard to do this part. It's like I say that a lot in Calculus 2. We did integration by parts. We did all the difficult integrals already. It's probably not that hard to do this part. But I want you to see why, like, we make the slice, the imaginary slice. We calculate its weight from its volume and its density. But in this case, the radius is the tricky part. Do you see why the radius of that in general would be 2/3 y? Tell me the y-coordinate of where the slice is. This will tell you the radius at that spot. That's what that does. That's why I put it here. Anyway, that's what we get when we're all done.